Like 2. Why didn't watch the 3?
That lab, they don't have lab. Oh, there's lab?
Yeah.
Oh shit. Because it was like 10, 40.
Yeah, he did kind of late, but yeah, there was. It was short though.
Yeah, because I was like, alright, like, not live streaming today since we didn't talk about that. Like, alright, no lab.
Christian finished it, but he did the same mistake as we did. With the, you know, with the curve, he did the same mistake as we did. So remember at the end, I saw that it was basalt. And he put the QLS. Which was no.
All right. Continuing on with our Columbia River basalts, Columbia River basalts lectures. We covered a fair amount in our first one on Monday about field data, the information that we have. I have some slides for you that I didn't get to. And there's also a couple of pages in the pink book that we didn't get to. So I'm going to go over those and show you some. Then we're move into sort of interpretations of what this information means to us. So the first thing, I gave you guys a bunch of numbers. We have, all of this basalt lava that erupted over 11 million years, 300 separate flows, and 3 miles thick in the Tri-Cities and all of that. 38, page 38, has a fairly simple diagram of the relative amounts of basalt. So there's a whole lot of freaking basalt. And I think I mentioned that the earliest fissures, this basalt came up out of cracks in the ground. And those first cracks in the ground were down in southeastern Oregon and even northern Nevada. And over time, they migrated up to southeastern Washington. The extent of our Columbia River basalts looks something like that. So we've got a lot of basalt, and the oldest cracks are down here in southeastern Oregon, and those cracks, those fissures, well, here, let's go to the diagram. There's 5 different, they're called formations. The Steens, the Imnaha, the Grand Ronde, which specializes in way too many silent E's, the Wanapum, and the Saddle Mountain. 5 separate formations. And so what's key here is these formations. Formations each has multiple flows. So multiple flows, that means multiple eruption events. That means multiple the cracks open up, the basalt comes out, the lava spills out. That would be a flow, but each formation has multiple flows, but they all come from, each formation has its own chemistry. So we can tell a basalt from the Steens formation, because even different flows within the Steens formation share a common chemistry. It's the same batch of magma, if you want to think of it that way. And each formation has its own set of cracks in the ground, has its own set of fissures. So that's one of the ways that geologists can differentiate between these flows. Like, okay, the Steens, which is, by the way, mainly in Oregon, that bottom 15%, the oldest of the Columbia River basalts, 15% or so, is mainly down here in Oregon, a little bit in Nevada, a little bit in Idaho. So that's going to be your Steens. Imnaha, not very big as these basalts go. It's still 10,200 cubic kilometers of basalt, which is a lot. But Imnaha, you're moving upwards. Imnaha, you're moving north. And then the big one, the Grand Ronde, is pretty much this whole thing. The Grand Ronde covers pretty much all of it. And then and that's 73% of the whole thing, the whole Columbia River basalt. And then we get pretty local with the last 7%. We have the Wanapum basalts, which are up in here. And the Saddle Mountains are pretty localized. It's the last little spurts of Columbia River basalt. I want to point this out. Saddle Mountains formation, when we say formation, we're referring to a set of different lava flows. This can get a little confusing because right outside our window we have the Saddle Mountains. When we say the Saddle Mountains, we're referring to the mountain range. And the Saddle Mountains are made of Grand Ronde and Wanapum basalts. And there's a little bit of Saddle Mountains formation up on the top of it. But we have layers from 3 different formations making up the Saddle Mountains. One other thing to point out, check out the ages. Steens, it took 100,000 years for the Steens and another 100,000 years for the Imnaha. 200,000 years to get 20% of this lava to the surface. The Grand Ronde, that's only another 400,000 years. And the Wanapum is another 200,000 years. So in 800,000 years, 99%, did I do my math right? Yeah, I guess so. Roughly, let's round up. Let's call it 1 million years. Let's say in 1 million years, about 99% of all of this lava spilled out onto the ground. And then we have another 10 million years or so of minor eruptions that make the Saddle Mountains formation. Okay, the other diagram that we didn't get to on Monday, I did it this morning. You guys probably tuned in. You probably already saw it, but we'll go over it again just to make sure. The anatomy of a basalt flow on 39. and I've been using this older book, and mine's color coded. I color coded everything in this book. I find it to be a really useful way to use that pink book is to color some of those diagrams in. But every single one of these basalt flows has certain features, and there are some features that are very common to all of them. So, cross-section diagram of a basalt flow, a single basalt flow within within a formation of the Columbia River basalt group. The most remarkable and the feature that stands out the most are the columns. Basalt forms when basalt turns from lava into rock. When it cools off, it naturally forms these six-sided columns. And when you stand up on top of one of these things, it's pretty remarkable. Sometimes they're five-sided, sometimes they're seven-sided, but usually they tend to be six-sided. But these columns are remarkable. It's like you're standing on top of a nature's honeycomb or something. These six-sided hexagonal features. The columns form at the top and at the bottom of the flow, and they are they're a result of the way the lava flow cools. So the way I did this morning, which I kind of liked, is we can think of the top of the flow and the bottom of the flow as a cooling surface, cooling plane. We'll call it cooling surface. And so the idea that we want here is this lava is coming in. Let's say it's coming in from left to right. It is flowing. It is red hot, orange hot, melted liquid magma, liquid lava. The place it's going to start cooling, the two places it will start to cool first are going to be at the outside, because the air is cold and the ground is cold and the lava is hot. So the inside is insulated, but the outsides begin to cool first. And as it cools, it shrinks. So just like a dried up mud puddle or something, as it cools off, these cracks begin to form on the surface. And as that cooling cools from the outside in, so you can kind of think of like a zone of magma hardening into rock, lava hardening into rock, and that zone of hardening moves slowly deeper and deeper into this lava flow. And as it does that, those cracks follow. They propagate downwards or upwards as it cools. But you've got this stuff in the middle called entablature. Which I don't know that the geophysicists have it really figured out, or the petrologists or whatever branch, I guess it'd be igneous petrologists. I don't know that they really have it all figured out, but kind of the best explanation that anybody has for why this funky entablature stuff happens is it's the last part of the flow, the last part of this individual flow that actually had any kind of movement to it. And that movement breaks up these cracks that are propagating inwards and causes everything to kind of twist up, and the stresses and all of that get weirded. But this is pretty typical structure for all lava flows, for all basalt flows. Now, we've got a couple other features on here. These down here, these circular things, are called pillow basalts, or pillows. And pillows only show up if the lava flow flows into water. From standing and I've got a slide, I've got a good picture of some pillow basalts. We'll talk about it a little bit more there. But this is a structure, it does not always show up. But if we find it, we know two things. One, we know we're at the bottom of the flow. If you've got standing water, it's going to be at the bottom of the flow. It's not going to be somewhere in the middle. So we know that pillows mean the bottom of the flow. And if we have them, it also tells us that there was water. So those are two things that pillows tell us. The thing that we will always have are these things called vesicles. I put an extra C in there. Why did I put an extra C in there? I hate misspelling words on the board. Guess I was thinking of icicles. Vesicles are little holes. And so we want to take ourselves back to when we were learning about different types of volcanoes and styles of volcanic eruption. Basalt is 45% silica. It's runny, low viscosity magma, low viscosity lava. And when it's orange and hot and melted, all the gases just bubble out into the atmosphere. But we've got this cooling surface at the top, and a skin will form on the top of our lava flow. That's the first thing to cool, and that's gonna, as the gases bubble up, they're gonna like bump their heads against this skin of rock that's formed, and they're not gonna be able to go any further. So this is gases piling up after the top has cooled. So every basalt lava flow is going to have vesicles, and vesicles always mean you're at the top of the lava flow. I don't know what I have going on with my color scheme here. It's weird, but you get the point. So if you were ever out hiking, out in the hills, and you notice all of a sudden all the rocks around you look like Swiss cheese with big holes in them, now you know the answer. Now you know what that is. Oh, I'm at the top of a lava flow. And as tends to happen, usually one encounters that kind of thing. Like say you're walking up a hill, going for a hike, you hike up the hill, you start down here, solid rock, start down here, you move up, solid rock, and then you come across rocks with holes, and you're like, oh, hey, it must be at the top of a basalt lava flow. And then you keep walking, and eventually you'll notice no more vesicles. And you know that you have moved from one lava flow into the next. You've gotten to the bottom of the next layer of basalt. So, vesicles, always know that at the top of the lava flow, if you encounter vesicles, pillows, not always there, but if they are, you know you're at the bottom of the lava flow. Entablature, you're in the middle of the lava flow. Columns, we give you one side or the other, top or bottom. So since this side of the board is all nice and clean, now seems like as good a time as any to try to coax this thing into life. See if I can do it with my phone. Go to Google Drive. There. Screen mirroring. Chest room 43. $91.22. Victory. That. Percent. Come on. Yeah, there it is. Okay. Columbia River basalts. Layer. We've got probably 7 or 8 different lava flows visible in this slide. Columns. There's some beautiful columns. That's out by Othello, a place called Drumheller Channels. It's a particularly great spot because you can hike up on top of this. You can walk across the top of the columns and really see that honeycomb shape. Some more columns. This is up at Frenchman Coulee. If you go up to Vantage and get on I-90 heading east, if you get on I-90 heading towards Moses Lake, take the Silica Road exit and hang a left, and then it's your first left. It takes you down into a really tremendously beautiful place called Frenchman Coulee. There's some like world famous rock climbing. All of these little white spots here are chalk from rock climbers' hands. Again, another Frenchman Coulee picture. This is a very unique. I just did that. I hate doing that. It's not very unique. If it's unique, it's unique. It doesn't even need to be very unique. That's redundant. This is a unique lava flow called the Rosa Formation. Unique because it looks like these crinkle cut fries almost. It's got these ripples. You can really see them over here. Geologists have not been able to figure this one out. Someday somebody will get a PhD when they can explain how it is that those crinkle cut fry shapes showed up in the Rosa. But you can see the Rosa also on 241, 243? 243. Highway 243 between here and Vantage. If you look off to the side, as you get closer to the bridge up there, you can see some Rosa formation. You can recognize it, but those weird ripples. Layers. Lava flow. There's probably 9 or 10 different layers. Pillow basalts, here we go. Here are some pillow basalts. You can see these rounded structures. There's one. There's one. There's one. This one's got a weird shape. But these rounded structures, and they're filled in between with this orangey, brownish, sometimes even yellowish clay stuff. And so here's the idea. Pillow basalts erupt underwater. The lava is flowing into the water, and water quenches, just like a blacksmith sticks something into a bucket of water to quench it. Water cools it very, very fast. And so you can imagine this like tube of lava it's hot on the inside, so it's still flowing, but the outside is getting quenched. It turns into volcanic glass. The outside, basically, it makes obsidian. And that the glass, but the rock on the inside turns into basalt. And over time, that obsidian weathers into these clay minerals and leaves the rounded blobs of basalt with all of this yellowish brown stuff in between. There's a really good, as a matter of fact, I think this photo is from just up the road. I think this photo was taken if you went up the hill towards GEOL, instead of like if you're coming to Mattawa, come over the bridge, you get off the freeway, you drive down the road, and then you either turn right and go to Mattawa, or you go left and you go up the hill towards GEOL. I think this is right there where you go around that bend going up the hill towards GEOL. Okay, here we can see a complete structure of a lava flow. We've got columns. We've got columns. We've got this entablature here in the middle. And when you zoom out, I think even you can probably, when you look at it like that, okay, take the lines away, start seeing it in the wild. If we go back to maybe that first one, even here, even zoomed way out, you can kind of start to see, okay, here's a flow. We can see kind of a line through the middle of it that's that entablature layer. You can see kind of a line through the middle of this one that's entablature. All right, geologic map of Washington. You guys are familiar with this. Saw that pretty recently. This brown, this is Columbia River basalt. And so anywhere that we see this tan is where the Columbia River basalts flowed to. Up here, around a little bit like this, and all the way out the Columbia River Gorge. There are Columbia River basalt flows. I'm sorry, this should go back down like this. There are Columbia River basalt flows that made it all the way to the Pacific Ocean. And as you guys know, we have those cracks in the ground down here in southeastern Washington. That was from their lab yesterday. Okay. So there's a lot going on in this diagram here, in this map. But I think it's good. I think that this is a good one for us. Washington, Oregon, California. Don't worry about the aeromagnetic anomalies. A couple of things to point out. craton boundary. And we'll build more on this idea, but we know where the edge of the North American craton is. It's right there. And then we've got, so here's the Steens dikes and the Steens lavas down here in southern Oregon. And then we can see the Monument Dike Swarm here and the Chief Joseph Dike Swarm. You don't need to know those names, but different swarms of these cracks in the ground. These are in Oregon. Here's our Washington, Oregon boundary. So a lot of dikes, fissures, cracks, whatever you want to call them, in Oregon, and a few in southeastern Washington. And a few over here in Idaho, too. But we can also see the extent of these lava flows. And it really does cover an awful lot of eastern Washington and Oregon. A little bit into, oh, that's Nevada. Right. We've also got some, there's a little foreshadowing for you, but we've got some old calderas from the Yellowstone hotspot. So, something to think about. Morning group, I hope you're watching because we didn't get to this slide this morning. Okay, there's another one. Steens, Imnaha, Grand Ronde, Wanapum, Saddle Mountains, basalt. You can see light blue, Steens is down here, Nevada, Oregon, a little bit of Idaho. Imnaha, over here, a lot in Idaho, still in Oregon. Grand Ronde, so that's our 73% of this thing. This one says 72.3, whatevs. All the green is Grand Ronde. We've got Grand Ronde all the way up here by Spokane. We've got Grand Ronde all the way out here at the Pacific Ocean. We've got Grand Ronde all the way down here in southeastern Oregon, over into Idaho. It covers the whole thing. The stars, I'm pretty sure the stars are the location of the fissures. Pretty sure. And then Wanapum. Now we're mainly in Washington, a little bit in Oregon. And Saddle Mountains, we're almost entirely in Washington. But still, even with the Saddle Mountains, we've got basalt flows that made it all the way to the Pacific Ocean. Hey. Hey, Apple TV, I advanced the slide. Here we go, please. There we go. So, this is a much more detailed version of the diagram in the book, right? Steens and Imnaha, we've got ages here. Saddle Mountains, Wanapum, Grand Ronde. And then this has like names of individual flows. Here's the Rosa. That's the one with the crinkle cut fries. It's a member of the Wanapum basalt formation. Priest Rapids, that's actually, I think, the one that's on the top of the Saddle Mountains. I'm not sure. But, and then this broken out because the Grand Ronde is such a short amount of time, but such a large volume. This is broken out into all of these different flows called members. Is that it? No? Okay, one more. Oh, there's a picture of one of these cracks in the ground where all this lava comes out. So we geologists know where they are today because they're full of basalt lava. But that doesn't look like this. We still have these kind of column shapes, but they're not vertical. It's not a flow. That was the crack in the ground, and that lava cooled, filling up that crack in the ground. So that's what a basalt feeder dike, a dike is another word for a crack in the ground, with lava in it. So there's a picture of a basalt feeder dike. And I have stopped sending things to this, and I'm not sure why it doesn't know that, but well, anyways, that brings me to the end of my slideshow, and that also, we've only got 5 minutes left, so I'm actually not going to dive into what I thought I was going to dive into. We'll save that for tomorrow. Just go ahead and wrap it up a couple minutes early. Anything from today that either of you fellas has like noticed, like out in, just in the hills around town, or driving around here and like, oh, yeah, I have seen that before. Did you kind of recognize any of those things, like the columns and the entablature, or maybe seen some pillow basalt somewhere? Yeah. Yeah. Well, next time you're out going for a drive or something, or next time you drive through the S curves or drive up the Vantage, take a look. Take a look up at the cliffs and see if you can spot some of those other features. Probably won't be able to see vesicles from the road, but you can definitely see layers of entablature. You can definitely see pillows if there are pillows to be seen. All right, live stream is going to come to an end now. End.